Good morning, good afternoon, good evening, everyone, and welcome to this next edition of our webinar series on optical coherence tomography. My name is Michael Leitner, and I'm Product and Sales Manager for OCT at Thorlabs. And it is a pleasure for me to introduce our today's speakers, my dear colleagues, Dr. Sebastian Schäfer and Dr. Dierck Hillmann, who will discuss the main differences between spectral domain and swept source OCT. Dr. Dierck Hillmann studied physics at the universities of Kaiserslautern and Bonn in Germany, and in 2008 he joined the Thorlabs OCT development team. While working for Thorlabs, he obtained his doctorate from the University of Lübeck and is now working for both Thorlabs and the university. His role includes software engineering, lecturing, and joint research with the group of Gerion Hüttmann. Dr. Sebastian Schäfer studied chemistry at the University of Siegen in Germany and graduated with a master's degree in 2008. After obtaining his doctorate in physical chemistry from the University of Hamburg in 2012, he did a two-year postdoc at the University of Rochester, and he joined Thorlabs in 2015, where he currently leads a group of application engineers and supports Thorlabs OCT customers with pre- and post-sales needs. Please note that questions can be posted throughout the whole course of the webinar in the Q&A section, which you can access through the icon on the top right of your screen. Well, Dierck and Sebastian, I'm looking forward to listening to your insights and would like to hand over the stage to you now.
Thank you for the introduction. Today I'd like to talk about the OCT technologies. I'll give a little bit insights into the theory of swept source and spectral domain OCT, and afterwards Sebastian's going to talk a little bit about the possible applications of both technologies. And just to give you an overview, I'll begin by talking a little bit about time domain OCT. Then I'll dive a little bit into the terminology of OCT, go to fourier-domain OCT, talk about actual swept source and spectral domain, the two possible implementations of fourier-domain OCT, and then go on to talk about all these specific system parameters and how they differ actually for swept source and spectral domain OCT. So first of all, the basics of OCT, the basic idea is very similar to ultrasonic imaging. You send a light impulse into tissue and you look at all the echoes of the light. And what you're going to see then is basically you try to measure the time difference where these echoes come from to really get an idea of how the tissue is built up. And this very idea was first shown by David Wang and James Fujimoto's lab in 1991 in their famous science paper. And the first realization of this is actually the so-called time domain OCT that I'm going to talk about first. And the main problem is that to really measure this impulse responses from the different depth layers is something you cannot really do because light is way too fast. And what you do instead is you make use of the coherence of the light source. So let's think of this very simple setup. You have a short coherence light source. You send the light into two arms, one with a mirror and the other one with a mirror that is actually moving. And you will only detect interference on the photodetector over here of the superposition of the two waves reflected from the mirrors if they have approximately the same length. So you basically find the position of the mirror, and you can also, of course, do this with multiple depths or multiple reflections coming from this arm. And the very principle behind this is called the coherence gating. So you gate all the light that does not come from within the coherence length of the laser. And that's one of the main ingredients of OCT, but there's a second one, and the second one is the so-called confocal gating, very similar to what you use in confocal microscopy. So you do not only bring the light into the sample, but you also create a focus in standard OCT, and the light from the focus position is then imaged back onto a pinhole, and only the light that comes from the very same two focus positions, the confocal part of the light, is really detected. If the light is scattered before this focus position, it's not going to be fully transmitted through the pinhole. If it's reflected behind the focus position, also much of the light is really rejected. However, you use a much lower numerical aperture, so much lower resolution compared to confocal imaging, so that you really get an entire range that you can really cover. And the technical realization usually looks similar to this one. You have a broadband light source, which can actually be a superluminescent diode. You then switch or couple the light into a fiber coupler where it's brought into reference and into a sample arm. The reference arm is scanned axially, which gives you all the different depths positions, and then the sample is scanned laterally, and the superimposed light is then again detected by a photodiode. In this setup, usually the fiber acts as a confocal pinhole, so that you don't really have to implement the confocal principle yourself, but it's basically already there. And as scanner, you usually use either a galvanometric scanner or a MEMS scanner, at least most commonly. And this brings me to the main OCT terminology. Well, one of these axial scans where you scan the reference mirror is called an A scan. And if you now also scan laterally, that's called a B scan, where you get really a sectional image of your sample or the tissue. And if you scan in the other direction, that's what's usually referred to as a volume. And you can also have an image where you basically only look in one depth layer, which is then called an en face image. Which brings me to fourier-domain OCT, because this technology was invented only a few years after time-domain OCT for the first time, but it really took a few years to take off. And the idea is as follows. You have a light source, and let's consider this scenario where you have a microsensor interferometer with two mirrors in both arms. And both arms should have the same length in this case. And now you change the wave number of the light, and independent of what wave number or what wavelengths you put into this interferometer, you will always detect positive interference in this photodetector, assuming there's no phase jump in the interference of the beam splitter. But what happens now is that if you change the position of this mirror and put in some difference there, now it depends on the path length difference between the original position and the new position, whether there's constructive or destructive interference, and it will also depend on the wavelengths. So if, for example, this distance here is from going to the mirror and back is 10 wavelengths, and you change the wavelengths by 1/10 of a wavelength, you will again have constructive interference, because now instead of 10, 11 wavelengths fit in there, but in the meantime, we will also observe destructive interference. And of course, if you increase this distance now, you go to 100 wavelengths difference. Just as an example, you only need to change the wavelengths by 100ths of a wavelength to get once through this cycle of destructive and constructive interference. And this principle was observed by several research groups in the 1990s. And what you can, of course, also do then, what they found out is that you can combine this, or you can also, of course, it's true for all other possible wavelengths difference, but you can also combine this. You can have a multi-layered sample, and then you have a reflection from the first layer, which makes an interference signal. You can have one from the second layer and one from the third layer. What you will actually observe is a superposition of these, and you can do a frequency analysis to really get back the depth information. And this actually has advantages over time-domain OCT, because in time-domain OCT, you only got interference at the points where your arms roughly correspond to the same path lengths. But here, for all the wavelengths that you detect, for all the wavelengths that you acquire data for, you will have interference for all samples of the layer, and that causes a sensitivity advantage that's quite significant over the time-domain OCT. And this was realized a couple of years after the first demonstration of fourier-domain OCT. And the basic principle is, again, the same. You have a reference arm, you scan your sample, you have a broadband, or you somehow have the detection of the different wavelengths, but you again use fibers, usually at least, to really get the confocal pinhole. And you again use a galvanometric or a MEMS scanner to scan laterally. And now we can have a look at the two different technical realizations. The first is the spectral domain OCT. To acquire this this spectrally resolved, this wave number or wavelengths resolved interference. In this case, you use a broadband light source, and then you use a spectrometer to basically detect that. And then you can basically also make this with a common path interferometer, where you have the reference arm and the sample arm put very close to one another, so that they are mostly fixed, and no fiber motion or anything similar will create this or will disturb this interference. And the signal is, of course, acquired over time. So the spectrometer is a line scan camera, which also limits the acquisition rate to a few hundred kilohertz, and it will acquire the signal over the time of an A scan for all the different wavelengths at the same time. Alternative is a so-called swept source OCT. In swept source OCT, you don't have a broadband light source, but instead you have a tunable laser, which will change its wavelength over time. So you get all the wavelengths in the interferometer one after the other, splits it into reference and sample arm. The sample arm is again scanned, and then the light that goes back is again split by the fiber coupler and runs through the circulator directly, and once directly on a balanced detection where the difference is built. And since there's a common part of both these interferometer exits, this will be subtracted, and you will only observe the interference. And the signal will, of course, build up over time, so you won't see it building up in intensity, but instead you will have all the wave numbers acquired one after the other. So it has this balanced detection. You will use digitizer instead of a line scan camera. Usually you get acquisition rates that are a little bit higher than spectral domain OCT. It can even get much higher to the megahertz rate. But what may also be necessary is a so-called K clock. Basically, that's a second interferometer that gives you the points where you need to do the sampling. Since for most lasers, these sweeps are not really reproducible, and you need to know when to acquire the next data point. A second interferometer will tell you that, which has a fixed wavelength in a Mach-Zehnder configuration, usually at least. And this is what an example of a B-scan of Scotch tape will look like. This is acquired with an SD system, a spectral domain system with a spectrometer. This is the Scotch tape from the side, and you see all the different Scotch tape layers in here. You also see the glue layers in between, where basically the signal dissipates. And you also have some artifacts that I'll talk later about in the top of the image. And you can really look in this Scotch tape in depth here. Which brings me to the possible parameters of OCT, and one of the most important parameters is actually the axial resolution. And this actually depends on how broad the spectrum is that you can acquire to observe your interference. You see this in this animation. As the spectrum gets smaller, your peak will get wider, and as the spectrum gets broader, you cover more wave number range, the peaks will get smaller. And that's closely related to the coherence length of the light source, where the connection between the power spectrum and the coherence length is the famous Wiener-Chinchin theorem that tells you about this. And this is of course also true if you have multiple signals. So here we see a spectrum as it would look like for 3 different depths, and as the spectrum gets smaller, you see that you can no longer distinguish these peaks as well. And as the spectrum gets broader, you can get more resolution, and you can better see the difference between the different layers. So this has technical implications for both SD and swept source. For SD systems, it's usually it's the spectrometer as well as the bandwidth of the light source, the superluminescent diode, for example, that will determine the resolution. In swept source, it depends on how far you can tune your laser, and of course whether the acquisition is running at that time. But those are the parameters that determine your resolution. And this also means that it's usually very much easier to get a good resolution, a high resolution. With SD systems, you can easily combine 2 superluminescent diodes with just with a fiber coupler, or you can use a supercontinuum light source, which also provides a higher resolution. It's not so easy for swept source because, well, you would need to switch gain media or the SOA in between the tuning, which is technically much more challenging. The second important parameter, of course, if we have axial resolution, so how good can we distinguish the different depth layers, is the lateral resolution. How good can we, in the scanning direction, distinguish different parts of the scan? And this is the model of a Gaussian beam, which beam waist W0, an opening angle theta, and the Rayleigh range ZR, which tells us how long the focus is maintained. And of course, as this beam waist gets smaller, your resolution will get better, and this depends on the opening angle theta. And there are 2 ways to distinguish it. We can either make the beam diameter that goes into the lens or into the objective wider, or alternatively, we can also change the focal length. Both will, of course, also have an effect on the Rayleigh range. So the better your resolution laterally, the shorter your Rayleigh range, and your Rayleigh range in OCT determines over what range you can really do optimal imaging with the optimal resolution and optimal sensitivity. And of course, the beam waist will also depend on the central wavelengths. In principle, there's no real difference in SD and swept source systems, except for maybe that the available central wavelengths may vary. And we need to keep an eye on the Rayleigh range because that really determines how deep we can image with the optimal resolution. Which brings me to the next parameter, which is the measurement depth of OCT. As mentioned, it can be limited by the focal range, but there's another thing to look, or two other things to look out for. One is the penetration depth. So if we have a specific sample, how deep can the light penetrate into the tissue or into the sample, and where is light still scattered back? And that, of course, depends how deep we can actually image into a specific specimen with a specific wavelength. The technical measurement range is somewhat different from that. So what we see here is that if we want to go to high measurement depths, the spectral fringe frequency basically gets to very high frequency. We need to be able to resolve this frequency to get to high measurement depths, and that determines finally how deep we can image. So how good we can resolve the high spatial frequencies. In SD-OCT, this will, for example, depend on the spectrometer layout. Again, the bandwidth, how many pixels does it have, so that we can still sample a high spectral frequency with the Nyquist limit. Also, of course, how good the spectrometer optics is in really imaging these fringes onto the spectrum camera. And for swept source, it's a little bit different. There's, on the one hand, the instantaneous line width or coherence length, which basically determines how much interference contrast do we have if we still, or if we move out of the or to higher frequencies, how much interference we can still maintain. Assuming that we stop the laser, or we could stop the laser, how much is the coherence length then? That's why it's called instantaneous. And how good can we have a look at that? And of course, there's the electronics, digitization frequency, the sweep rate, and the electronic filter, which need to match to the measurement depths. But those parts are fairly easy to obtain. And so what happens if you either have not the perfect coherence length or coherence function, or not the perfect spectrometer imaging, you will lose signal over depth, which is called roll-off in OCT. And roll-off in generally is higher for SD systems, and you have a, well, rather theoretical limit if you have a fill factor of about 1 for the camera, so the camera pixel size is the maximum, so that you don't lose light. You will at least lose 4 dB of sensitivity over the entire measurement range. Usually it may even be higher than that. For swept source systems, however, you can have a single frequency layer there that's tunable, which will have a much longer instantaneous line width or coherence length, really showing zero roll-off within a certain measurement range. And so swept source measurements can by far exceed the technical range of SD systems. And then another parameter that may be important to some applications, I will only go briefly about this, is the so-called phase stability. OCT scans will not only have the information about the intensity, in what depths, what intensity occurred, but also the information about the phase. What's the phase of the light that we can see? And usually these spectrometer-based systems will have a very stable, well, mechanical, stable acquisition system, so that you won't really notice anything about phase jitter. Whereas for swept source, everything needs to be controlled very tightly in order to get really a phase stable measurement, because there can be jitter in triggering, in the laser sweep that can maybe not be perfectly reproducible, or there's disturbances in the K clock, which will cause phase jitter or may cause phase jitter in swept source. And also there's this interferometer. I mentioned that the SD system can oftentimes be realized with a common pass interferometer. A common pass interferometer will be more phase stable than a fiber-based interferometer, where you really have fiber motions that can really change the phase of your sample or reference light for that matter. And then there's a little bit about balance detection and artifacts. This is a little bit simplified, but we have the OCT signal, which is usually the interference of sample light with reference light. But what we can also think of, that sample light will interfere with itself. And also, well, that's mostly the intensity of the reference light we observe, but we could also think of reference light interfering with reference light. And of course, we can have the change of the role of sample and reference light interchanged. And those will create 4 signals in each OCT scan. And in an SD system, this will look as follows. We have a DC part, we have a signal part, we have the conjugated signal, and we have the autocorrelation signal, which shows up close to the DC part. Basically, the first peak of the sample signal in this case served as a second reference, causing these artifacts over here. And in SD systems, those are there unless you do additional measurements or do have a little bit more effort to get rid of those. So for SD systems, it's not really straightforward to distinguish these signals, but the balance detection in swept source OCT, the autocorrelation signal and the DC signal will have the same sign when those balance detection input signals are subtracted, so that only the signal remains. And we see this here in this example. This is again Scotch tape, and for the SD system, we have this autocorrelation noise on top, whereas for the swept source system, this vanishes. And we also see the other features that I already talked about here fairly nicely. We see that those layers can be better distinguished in the SD system because it has the higher axial resolution, but we see that the overall measurement range that's possible with swept source system is much higher in this scenario. And another feature I'd like to talk about is the so-called phase washout that occurs in SD systems and the corresponding Doppler shift that will occur in swept source system. So let's assume we have a signal from a mirror, in this case again, that moves slightly. So we see that due to this small motion, the phase, you can see this here on the edge, it will change slightly. And let's assume that this happens during the acquisition of a single A scan. What will happen is that the signal will average each other out because we have different phase situations that will be integrated upon, and in this case it's not shown as integration but rather as averaging, and the peak will lose its signal strength. It will still be at the correct position, but it will be much weaker than it was originally without this axial motion in there. So for swept source, something different is happening. So for swept source, this is again the situation. What happens now is that the signal is acquired over time. And as the phase changes in the background, we see that actually the wrong frequency is captured. We keep the entire signal, but it will be slightly shifted axially. So it may appear at the wrong position. And that happens in both. We have in both scenarios this feature that motion may have artifacts more severely in SD systems, but in swept source systems, if the if the A scan time is roughly the same, we will also usually see some artifacts. So to give you a final overview of this part, and afterwards Sebastian's going to talk about the possible applications of both spectral domain and swept source OCT. Usually we have artifacts, and in swept source we don't have autocorrelation artifacts. In spectral domain we have these autocorrelation artifacts, but otherwise the spectral domain signal is much more stable, which allows us to much more effectively get rid of some artifacts that we have in the A scans. Stability also comes in for the phase stability, so spectral domain will provide better phase stability, whereas for swept source, phase stability is much more challenging. For spectral domain, we always have this compromise of resolution and measurement depths, but that allows us also a better axial resolution, whereas for swept source, a better measurement range is possible, higher measurement range, and also better roll-off is possible, so it does not have to be there in principle. And for swept source, we also have higher acquisition rates up to several hundreds of kilohertz or even megahertz rate. However, most of these differences are rather technical and not really fundamental, maybe with the exception of that you have finite pixel sizes in SD system, which cause some 4 dB roll-off. And so as technology develops, things may change in these regards. So this is all typical scenarios, but it's not fundamental scenarios. Most of the stuff that's possible with spectral domain is also to some extent possible with swept source. And so this concludes basically my part, and I will just hand over to Sebastian to give you examples on on what that will look like.
Thank you, Dierck. Now that we learned about the two predominant OCT technologies, I want to talk about when to choose which technology and what their advantages are. And I will show some examples from widespread applications in research and industry. And I want to start by looking at ophthalmology, because that is really the biggest market for OCT. And over the last 2 decades, OCT has established itself as an essential tool in ophthalmic diagnostics and during ophthalmic surgery, and nowadays can even be found in small ophthalmic practices. And there are medical OCT systems on the market for different applications, and here I want to just show you where you typically image in the eye. So here I have a sketch of an eye, and one application is retina imaging. Retina, this is the yellow layer back here. And that can be imaged for example, for diagnosing glaucoma and age-related macular degeneration. Then we have imaging of the anterior chamber. The anterior chamber is over here with the cornea and iris and lens. And here you're often interested in the geometry. On top of that, we can also measure the geometry of the anterior chamber and the axial length of the eye, which is then called ocular biometry. And this is often done prior to cataract surgery. Now I want to show you some OCT images. Here again, we have the sketch of the eye for you as a guide. And I want to start with retina imaging. And here we're typically interested in the retina back here, closer to the optic nerve. And here you can see two OCT images. On the left side, I'm showing a spectral domain OCT image, and on the right side, a swept source OCT image. And those images are tilted by 90 degrees. So basically the cornea would be up here. And in retina imaging, you're often interested in measuring the individual layers and also in knowing the layer thicknesses. On the left side of these two images, so in both images, we see a model retina. It's not a real human retina, it's just a model retina, but it shows pretty well what you can see in OCT. And you can see some layers in both images, and on the left side, you can see that the structure is a lot finer, while on the right side, for swept source, it's a lot grainier. But you can see that the advantage that Dierck described earlier, that you have a larger imaging depth in swept source OCT, you don't really see that advantage over here because you're only interested in a very thin layer. And after the light penetrates the tissue, by a few hundred microns, all the light vanishes. So you don't get any advantage over here. So most people would choose spectral domain OCT in this case if they're interested in discriminating between the layers, the individual layers, and want high resolution. But swept source OCT can have its advantages in this application, especially if you're interested in acquiring 3D images that require you to acquire the data really fast because the eye is constantly moving, so you want to acquire data fast. And in that case, swept source can be the suggested technology just because it can acquire data faster. Now I want to look at another ophthalmic application, and again, we're looking at the same model eye, so it's not a real human eye. This time we look at the anterior chamber, and it's tilted by 90 degrees again. And just let's look at this swept source OCT image over here. We have the cornea up here, we have the iris here and here, the top of the lens here, and the bottom of the lens here. And with swept source OCT, you can image the whole anterior chamber. This is no problem. And on top of that, you see some additional room down here. With the right OCT system, you can also go all the way to the bottom and image the retina. And with spectral domain OCT, you're really limited to the anterior chamber. This is pretty much the maximum you can get with spectral domain OCT. So why would you be interested in imaging all the way down to the retina? Well, just imagine there's a cataract surgery, for example, and the lens is cloudy and you want to put in an intraocular lens, take out the cloudy lens. You can measure the geometry of the anterior chamber, and that gives you the refractive power of the eye, but you still don't know where the actual retina sits because you want to focus on the retina. So you need to know where the retina is in order to not focus in front or behind the retina. So in that case, you would typically use swept source OCT because you can achieve a much larger imaging depth. As Dierck mentioned in his part, the depth in swept source OCT depends just on how many data points can be acquired during one sweep. And by increasing the speed of the data acquisition or by slowing down the sweep rate of the laser, you can achieve a larger imaging depth. Combined with a large coherence length, for example, of the Thorlabs MEMS pixel swept source laser, this allows for OCT imaging even on the cubic meter range. And what you can see here are some images that were acquired by Ben Potzet and James Fujimoto from MIT. On the left side, you see just photographs of a mannequin and a bicycle, maximum intensity projections of these images. And then over here, you see actual OCT images. And you can see that you can acquire data on the meter range in all dimensions. While this is a fringe application, it shows the capabilities of swept source OCT technology and also opens the door for future applications like LiDAR. Now I want to make a cut and talk about another application, vibration analysis in particular. First, what do we mean by vibration analysis? Basically, you look at the axial signal and you look at it over time. And that allows you to pick up vibrations in your sample. And there are actually a lot of examples where this is of interest. And I'm just going to name a few here. One is what is often referred to as the mechanics of hearing. For example, imaging and then analyzing vibrations in the cochlea and tympanic membrane. And here, researchers are usually interested in vibrations that are below the resolution limit of OCT, so much smaller than 1 micron. But by looking at the OCT phase, one can still track these minimum axial vibrations. Then there's laryngoscopy, the vibration of vocal cords. And here you have vibrations on the order of hundreds of microns or even millimeter. Then there's elastography, where you want to measure the elasticity of tissue or any other sample. And this is often done by exciting the tissue and then looking at how the wave propagates across the tissue. And this can tell you something about the elasticity of the tissue or your sample. And there was actually an interesting webinar in January by Brendan Kennedy on the topic of elastography. If you want to, you can go to the Thorlabs website and watch that webinar. On top of that, there are some other industrial applications. Now, let's look at some of these vibrations in OCT. So here we're looking at a frequency of a few hundred hertz and with rather large amplitudes of a few hundred microns. I'm going to show you a video that was acquired with the Spectral domain OCT system, and here you can see some layers of Scotch tape that were taped on a loudspeaker. And then the volume was slowly increased, and so you will see the amplitude of the vibration in OCT increase. So let me start playing this video. And now you can see a small vibration and it gets stronger and stronger. And for really strong vibrations, you can see that at the top and the bottom, you can see the individual layers of the tape. But in between where you have really strong movement, the OCT signal disappeared. Now this was for a spectral domain OCT system. Let's have a look at the same tape with a swept source OCT system. First, what we notice is the resolution is different. Now we do not see the individual layers as crisp anymore. But now let's look at the video of the vibration in swept source OCT. We see the vibration getting stronger and stronger. And now, even when we have a really strong vibration, we see that we do not lose any signal in depth, even when we have this strong movement. The reason for the decreasing signal intensity in spectral domain OCT is the so-called phase washout, which has been discussed in Dierck's part already. So for that reason, when we have really strong vibrations, we typically suggest swept source OCT because there's no phase washout and you do not lose your signal. Let me give you an example of where this could be interesting. In laryngoscopy, one looks at the vibration of the vocal cord. And here we have the vocal cord of a human. These data were acquired by the group of Brian Wong at UCI. On the left side, you see the OCT data, and on the right side, you see a video image of the sample. And you see a red aiming laser over here. This just indicates where the OCT data were acquired. Now let me play this video. And you see that the frequency changes, but the intensity does not change. So this is a good example of using swept source OCT to acquire strong vibrations and not lose any OCT intensity. On the other end of the spectrum, researchers are interested in tiny vibrations in the hearing apparatus. Here you can see some images that were acquired by Marcel van der Heijden from Erasmus University in Rotterdam. And they looked at the organ of Corti in the ear of a gerbil. On the left side, you can see an OCT image. And here you see a sketch of what you can actually see in that OCT image. You can already tell that these structures are really tiny, and it's you cannot see all the fine structure of the organ of Corti in the OCT image. But it helps you to navigate these really tiny structures. And then one can look at the vibrations at different positions. So here we see the intensity of the vibration after the ear or organ of Corti is excited at different frequencies that are on the x-axis here, and different locations shown here. And you can see that the different locations react differently to the excitation. And thanks to OCT, we now know how the different locations or spots in the ear react to excitation. And these vibrations are really small. They are typically in the nanometer range, so we need the OCT phase to actually resolve these tiny vibrations. And in this case, we would recommend spectral domain OCT for two reasons. One is spectral domain OCT gives you a higher axial resolution, which makes it easier to image these small structures and find your way around the ear. And on the other hand, spectral domain OCT systems are inherently phase stable. Now, I want to show you one last example, and I want you to think of the following setup. The probe is mounted on a robot and moves to different positions. This can be in a research lab where you have a large sample and move the probe head around, or this could also be on a production floor where you use OCT for quality control. And these are the two setups that Dierck showed earlier, the common path interferometer and the dual path interferometer, where the common path interferometer is typically used for spectral domain and the dual path interferometer is used for source OCT. And in the common path interferometer, you create the interference pattern in the probe head, and you have just a beam splitter, and this happens before the light is coupled into the fiber. So you can imagine if you move the probe head around and you move the fiber, this does not affect the interference pattern that you generated here. Whereas over here, you have two fibers, one going to the reference and one going to the sample arm. And if you move either one of these two fibers around, for example, by moving the probe head, you will change the light that goes into the fiber coupler where the interference pattern is generated. So let's look at how that may look like. Here we can see an OCT image of a plastic sample that is being imaged by swept source OCT. And now the fiber is moved, and let me show you the video. Once you move the fiber, what you see is the polarization of the light may change. That leads to some artifacts, these stronger lines, and you also see the image moving up and down, and that is despite the sample and probe being fixed. And this just happens because the sample fiber changes in length. Now let's look at the same sample in spectral domain OCT. And when you move the fiber here, you see that only small intensity changes within this plastic can be seen. So for that reason, one would typically recommend a common path interferometer if the probe head is moved around a lot. And that is often or typically found in spectral domain OCT. Now I want to spend a few minutes talking about what we do at Thorlabs with regards to OCT, and then we will open it up to questions. We have different offices around the world that manufacture items that are being used for OCT by researchers who build their own system, but also by the Thorlabs OCT group in Lübeck. Let me start by introducing some of these groups. We have a group in Canada that makes fiber networks for OCT. We have Thorlabs Quantum Electronics in Maryland in the US, and they make superluminescent diodes for spectral domain OCT and MEMS VCSEL lasers for swept source OCT. Our team in the UK makes motorized stages that can be used to move a sample underneath the OCT probe head, but also to move the reference arm of an OCT system. Our group in Munich makes balanced detectors. The housing of our OCT systems is made in Shanghai, China, and you can actually also buy this housing off of our website. Our group in Sweden makes telecentric scan lenses that are optimized for OCT, and all of that comes together in Lübeck, where we make complete OCT systems. Let me tell you a bit more about this group. We are a spin-out of the University of Lübeck, and we have 14 years of experience in developing and manufacturing OCT systems. Our systems are used around the globe in academic and industrial research, and we also supply several OEM customers with our systems. The hardware and software manufacturing, hardware and software engineering, as well as manufacturing, are done at our office. We also do the application and technical support, and we do the sales. We have 35 employees, and we have an in-house applications lab where we do sample testing. And let me tell you a bit more about that last point and what that means for you as our customer. We analyze your project with you to identify the best system configuration. We offer sample testing at 4 locations on 3 continents, that is in Tokyo, Japan, Shanghai, China, in Sterling, Virginia in the US, and of course in Lübeck in Germany. We are the only manufacturer of OCT systems that offers both technologies, swept source OCT and spectral domain OCT. And that means that we can verify independently which technology is the best for your individual application. We have a dedicated applications and OEM team with many years of experience, and Thorlabs sources most of the components from within Thorlabs. And that just allows us to be flexible when it comes to requests for OCT systems with special specifications. And that also allows us to source components for your OEM from within Thorlabs. Let me show you our portfolio for complete OCT systems. We have 5 series in total. That means we have 2 sub-source OCT series. We have the Atria series at 1060 nanometers and the Vega at 1300 nanometers. And for spectral domain OCT systems, we have the Ganymede series at 900 nanometers, the Telesto series at 1300 nanometers, and the polarization sensitive Telesto, which is also at 1300 nanometers. And while I'm talking about polarization sensitive OCT, I want to mention that my colleagues Matthias Puus and Pablo Sticker will give a webinar on the topic of polarization sensitive OCT on May 26th, and you can sign up on our website for that webinar. And with that, I want to thank you for your attention.
Thank you very much for these really interesting insights. And we already have several questions from the audience. The first question is for Dierck. Matthias Gerlach asked if the confocal gating doesn't require short coherence lengths.
Well, yeah, thank you for the question. Usually you could do a confocal gating with either a short coherence length or a long coherence length. What you might require, depending on how small your pinhole is, that you really get spatially coherent. So you'll have a spatially coherent source, but you'll have you can have a short coherence length still that you can use for OCT.
Another question for Dierck. Ashish asked, what does it mean if phase washout in SS-OCT is mix of both effects, that is displacement of FFT peak as well as change in amplitude of the peak?
Yes, that's a good question. Well, the change in amplitude will be relatively small for a swept source system, but what happens is if you write down all the terms that occur for a motion during the sweep, you will see that they're nonlinear terms. So your peak will get broader and will lose a little bit in signal. And also what might happen is actually that if you really move way too fast, you will could possibly, I don't think that happens much, but you could possibly even lose the signal due to the very same reasons that you have for an SD system, that you acquire multiple phases and average those. But then your frequency will basically be out of the measurement range, so that you don't really get that anymore.
One question for Sebastian. Will asked, why does SD OCT have a higher resolution than swept source OCT? Can swept source OCT get the same resolution by using same bandwidth?
Yes, theoretically, swept source OCT can get the same resolution by using the same bandwidth. It is just technologically, it's a lot harder to get multiple swept source lasers to work together. And in spectral domain OCT, it is really simple. You just take one SLD and another SLD, and you use a fiber coupler to couple them together to get one broad spectrum. So it is mostly a technological limitation, or it is a limitation in a sense that it is just much harder to do it. So usually people use spectral domain OCT when they want a high resolution.
Pilar is asking, could you please expand a little on how the Rayleigh length is related on how deep we can image with optical resolution? Dierck, would you love to answer?
Yes, thank you. So the thing is, outside the Rayleigh length, we have two things. We first of all, our PSF getting broader, just because we're defocusing. It's the same for microscopy or other techniques. And the second is, since we use this confocal gating, at least with standard scanning OCT, we have a point or a focus beam into the sample or tissue, and we have the backscattered light imaged again through the pinhole. And as we move out of this focal range, out of the Rayleigh range, the light will not couple back as efficiently into the pinhole or the fiber in this case, and that's why we'll lose sensitivity. So to have really optimal resolution, we're restricted to the Rayleigh range, really, but it does not degrade really quickly afterwards. So once outside the Rayleigh range, you'll lose a factor of √2 or something similar. And if you go further, you will lose more sensitivity and more resolution. I hope that answers the question.
The next question, for the swept source OCT, if the receiver and ADC bandwidth is sufficient, what is the resolution, the relation between A-scan rate and maximum imaging depth, if there is any? Dierck, do you want to answer as well?
Yes, sure. Well, that's, of course, as you've maybe by now seen in Sebastian's talk, you can really have high measurement ranges with swept source OCT, even up to meters. And the actual limitation that remains is the coherence length, the instantaneous coherence length of the laser, if you really acquire the data sufficiently fast. And so you can really go up to very, very long measurement ranges. So there is no further limitation, yes.
Can you comment on the amount or type of speckle and the relation between that with the type of OCT, so spectral domain or swept source? Maybe you again, Dierck?
Sure. I wouldn't expect there to be a fundamental difference in speckle for swept source and SD systems. What we may expect, though, is that, speckle usually originate because you have some random interference from scatterers in the sample or in the tissue. And the better you're able to resolve those scatterers, really resolve them, the less speckle you will get. So things that you can really resolve where you don't have the phases interfering randomly, that's something where you can really get there without a speckle. So if you have a mirror, for example, that's very flat, you won't have speckle like that. And so you will notice that the higher resolution gets, the less speckle you see. And that means actually SD systems can have lower speckle size. But if the resolution and the bandwidth is identical, I would expect there to be the exact same speckle, and it even look fairly identical in that case.
Okay, thank you. Benedict and an anonymous attendee asked why common path is less used in swept source OCT. Sebastian, do you want to answer this one?
Yes, thank you for the question. It is basically because we cannot easily realize that with balance detection. So you create the interference pattern in the fiber coupler that then directly leads onto the balance detector, and you would have to use the outputs of the beam splitter in the probe head, but then everything, your detection would be in the probe head. I hope that answers the question. You cannot easily just direct it through the fiber onto the balance detector. That's maybe an easier explanation.
Margarita asked, at the start, you mentioned Fourier domain has sensitivity and time advantages over time domain OCT. Are there any applications for which time domain OCT is preferred? Sebastian or Dierck, who would like to answer this one?
Shall I? Do you want?
Go ahead.
Well, there are currently, I guess, there are not many time domains used. That becomes different if you go to different technology. So if it's no longer scanning OCT, but there's, for example, this full field OCT, where you can get to really high resolutions, and that's where people still use time domain OCT. I'm not aware of many people still using time domain in a confocal scanning scenario, but there may be some edge cases where it's cheaper, or maybe you just need a very shallow measurement range that you can really scan quickly over the depths.
Pilar asked a second question. Could you please comment a little bit more on how the confocal point spread function contributes or alters sensitivity throughout the imaging range, on factors including the PSF and the relation with the various noise sources?
So the PSF, I mean, one can even analytically get the PSF for different depths and calculate it, and also have, I guess, in the old confocal theory really predicts how the intensity will behave if you walk through the focus. I'm not really sure what noise sources one would expect or what they could influence this scenario. I mean, you'll lose sample light, but as long as you're really in the optimal scenario where you're shot noise limited, you will still, basically not get any additional noise in there. Just lower your sensitivity because the detection is no longer that efficient.
Okay, Mike is asking, why is the axial resolution lower for swept source OCT? Sebastian? I think we had this already.
Yes, I mean, we already talked about the bandwidth, and basically the bandwidth and the axial resolution are connected, and the broader your bandwidth, the better your axial resolution. And as mentioned a few minutes ago, it is a lot harder for swept source OCT to get a broad bandwidth, because for spectral domain OCT, you really just connect a few SLDs and then you have a broad spectrum, and that just gives you the really high resolution that you can achieve with spectral domain OCT.
Okay, the next question. For swept source OCT, if the Dierck card signal is saturated caused by the strong reference arm light, can we use a high pass filter to solve this problem?
Why don't you use less reference light? Or a different amplification level?
Yeah. So I would also say just a high pass filter. I mean, the balance detection should get rid of the DC part of the light. So a high pass filter after balance detection is no longer really necessary. If you don't use a balance detection, of course, that may help to some extent. But only to some extent. Once the modulation gets too high, it's basically that this will no longer work.
Okay, and the last question that we have here, for swept source OCT, if the scan rate goes very high, so for example 400 kilohertz or some research towards 1 megahertz, I saw in Thorlabs listing that the imaging depth was listed about 2 to 3 millimeters. Was that limit solely from receiver or ADC bandwidth? And could it still provide, for example, 10 millimeters imaging with high bandwidth?
Yes, so I think I'm going to answer that question. The imaging depth that we list for our lasers on our website is really just assuming that you use our provided K-clock trigger signal and a certain data acquisition card. And if you do not use our K-clock signal, you could, for example, just generate your own K-clock trigger signal, or you could just monitor the K-clock trigger signal, which is sometimes called the dual channel approach. And in that case, you can achieve a higher imaging depth. It's not inherently that the laser cannot do it. It's really about acquiring the data points to get that high imaging depth. And how do you do that with the hardware? So yes, it is possible to get a higher imaging depth.
Okay, 2 more questions came in and we answered them before we close. Matthias Gerlach asked again, would it bring any advantages in using a supercontinuum laser for spectral domain OCT?
Yes, you can do that. You will get a really broad spectrum. You can get a very high resolution. Supercontinuum lasers typically have a high power, which also means that you get a good contrast in your image. One of the drawbacks is it is expensive. But yes, it is possible.
And your spectrometer probably needs to support the bandwidths. So.
Yeah, of course. And the question also becomes which part of the spectrum can you use? You will not be able to use the whole spectrum because your fibers will probably not transmit the whole spectrum. It's typically really broad, the spectrum. But even using 300-400 nanometers of the spectrum will get you a very good axial resolution.
Okay, and the last question, is the lateral resolution in OCT worse than in standard confocal microscopy? If yes, why?
Well, okay, Dierck, go ahead.
You can also, so yes, usually it will be, just because you use a different numerical aperture. So usually you'll want a Rayleigh range that's, so in confocal microscopy, you want a Rayleigh range that really sections your sample. So you want to have a Rayleigh range at the maximum possible NA to really get shallow depths sectionings, basically. And for OCT, you want to have a high measurement depth or a higher measurement depth. So you go for a lower NA. Lower NA means lower lateral resolution, or not lower, worse lateral resolution. And therefore, it's not as good in that case.
And maybe one more addition. Typically in OCT, we use near infrared light,
sure,
which will also give you a worse lateral resolution than the visible light that is typically used in confocal microscopy.
Yes.
Thank you very much, Dierck and Sebastian, and many thanks to everybody for attending our webinar today. Please note that our next OCT webinar is already scheduled for May 26.